about one-to-one functions. You remember a one-to-one function means that every input, every item in the domain is mapped to a unique output or unique item in the range. And so we're going to talk about today what can we do if we know that a function is one-to-one. Okay, so if a function is one-to-one, so if you have some function f, it's a one-to-one function, we can find its inverse function. The inverse function is the function that maps in the opposite direction. So if you have f, there it goes, and that f is taking items from this set and mapping them to this set. Is it? Mapping it to here. Then f inverse is doing the opposite. It's going to map backwards from that one to that. That is what the inverse function does. That is what it is. This is a -1 up here. I'm going to clean it up because it's kind of just looks like a weird symbol. But that is what an inverse function is. The reason that we need the original function to be one-to-one is because if it's not, and we find the inverse, that inverse, it'll be a relation, it won't be a function. Because it'll have one item mapped to two different items. So that is why we want that original function to be one-to-one. So let's read this off. Suppose that f is a one-to-one function. Then corresponding to each x in the domain of f, there's exactly one in the range. This should be one input to one unique output. And corresponding to each y in the range of f, there's exactly one x in the domain because f is one-to-one. Same thing. The correspondence from the range of f back to the domain of f is called the inverse function of f. And we symbolize that with f raised to the -1. I always think about, remember when you raise a fraction to the -1 power, it like flipped it, it inverted it, so it's the inverse. And that is what we're going to be talking about today. Any questions on that? So when you do the inverse, basically what it's going to do is it's going to swap the domain and the range. The domain of f is the range of f inverse. The range of f is going to be the domain of f inverse because the mapping is flipped around. Okay. So if we're given a function written as a set of ordered pairs, that means that our function maps -3 to -27, -2 to -8, -1 to -1, 0 to 0, 1 to 1, and 2 to 8, and 3 to 27. What is the domain of that function? Let's call it f. So what is the domain of f? If I remember how to do that? It's going to be all those inputs, so -3, -2, -1, 0, 1, 2, and 3. What is going to be the range of that function? Oh, sorry. There's a bug on my screen. It's going to be all the outputs. So it's going to be -27, -8, -1, 0, 1, 8. So that is going to be our range. If I asked you, using that, to tell me how would you define f inverse? The inverse function of that one.
With the output is good.
Yeah, so what are we going to do? Instead of -3, -27, what are we going to have? Yep, it's going to map it backwards. So it's going to take negative 27 and it's going to map it to negative 3. And then we would just do that for all of the ordered pairs. So instead of negative 2 being mapped to negative 8, it's going to be negative 8 mapped to negative 2. The negative 1 was mapped to negative 1, so we end up still with negative 1, and the same thing for 0 and 1. Those aren't very exciting. But instead of mapping 2 to 8, our inverse is going to map 8 to 2. And instead of mapping 3 to 27, we're going to map 27. So run out of room for 3. And I'm just going to close that off there. So, any questions on that? First off, before what is the domain of my inverse function going to be? Be negative 27, negative 8, negative 1, 0, 1, 8, and 27. It's the range of the original function. It's the range of f. And what is the range of my inverse function going to be? Negative 3, negative 2, negative 1, 0, 1, 2, 3, which is the same as the domain of my original. Any questions on that? All you're doing is you're just swapping the input and the output. Instead of mapping the input to output, it's mapping it backwards from the output back to the input. And you can see that here, it's kind of the same picture I drew earlier. Get the range of f, the domain of f is mapped to the range of f, but the inverse function is going to take it backwards. And I think I have a note under there too that I didn't show you also. Let me get a note sheet. Oh, there we go. Didn't like that. There we go. Oh, it's the same thing. Just didn't want to make sure I understand. So the domain of f equals the range of f inverse, and the range of f is equal to the domain of f inverse. Now, it doesn't seem like that amazing, but if you think about when we're talking about functions before, we have a process to find the domain of f, right? Right? We were doing that the other day when we were talking about composite functions, right? We were finding their domains. But do we have a method to find a range of f? There's one type of function where I guess it's a couple of functions we did talk about their range. We talked about the range for quadratic functions, and I mean the range for linear functions. We kind of talked about those a little bit. But for like just functions in general, we never really talked about how to find the range, and it's not super easy to do if you ever kind of dive into it and look into it. But now that we can find the inverse and then find its domain, that would allow us now to be able to find the range of our original. This is only going to work if our function is one-to-one, so we can't do it for everything, but it does give us a means to find that, and that's what's really nice about it, because it's something that we really couldn't do before. Any questions on that? All right. Now, I did say that we were going to tie it back to the composite functions. This is where it ties back to the composite functions. If you do f, there we go. I guess this would be f inverse composed with f of x. So f inverse of f of x is just going to equal x. And if you do f composed with f inverse of x, you're also just going to get x. So if you do the composition of two functions and you just get x, those functions are inverses of each other. If you've done the homework on 6.1, there's some problems towards the end, I think, where it's like find f of g, find g of f, and make sure they're the same. And every time you do them, you get x. It's because all those functions are inverses of each other. That's what we're trying to lead you towards to make kind of discovery of what's happening. Okay, so if we look at two functions, it looks like we got f of x is equal to 2x, and we want to find what's f inverse. Well, what will make 2x equal just x? Multiplying it by 1/2. So f inverse here would be 1/2 x, which we're going to learn a better way to do this in a little bit, but this is one method you can use for simple functions. What would you have to compose that function with to get this x? And you can figure out the inverse after. Any questions on that? So we can use that if we're given two functions. They say f of x is equal to 1 over x minus 1, and we propose that f inverse is 1 over x plus 1. But we want to make sure. And so if we want to verify that these two functions are inverses, we're going to find f of f inverse of x and see if that equals x. And we're also going to find f inverse of f of x and see if that's equal to x. The two things we want to do. Doesn't matter which one you do first. No, not really. And there's some thoughts that if one of them works, they should both work. But I think it's a good idea to do both of them just to check. Just to make sure. All right, so let's do the first one first. Let's do f of f inverse of x first and see if we get x there. So f of x is 1 over x minus 1. We're going to replace that x with f inverse. So we're going to have 1 over f inverse of x minus 1. I guess I should put equals here. And we know what f inverse is. It's 1 over x plus 1. At least that's what we think it is. We're going to see. And so let's substitute that in. So we'll have 1 over x plus 1. Let's group that for right now. Minus 1. Just to group it so we can see where that substitution's happening. It's not super necessary in this case. All right, so let's rewrite it. We'll just drop that grouping. So we'll have 1 over x plus 1 minus 1. So the plus 1, you got a question? Because it's not multiplication. It's this minus 1, right? So it's still going to be this minus 1. If it was multiplication, then yeah, you would. And so this plus 1 and minus 1, that's going to be 0. So they cancel out. And so we end up with 1 over x. Does that equal x? Can we do something to get it there, maybe? What do you think? Why would we multiply by x? You're all right. I'm just curious of how you came up with that. And why did we do that, Jeff? Do you remember? Yeah, so we got this fraction within a fraction, right? You got a fraction in this fraction, and so what we're going to do is multiply the numerator and the denominator by whatever that denominator is there. So we're going to multiply this by x and this by x. And so we're going to end up with, and let's do the steps. So that's 1 times x, that's going to be x up here. Then we'll have 1 over x times x, which those x's will reduce. And so you're just left with x over 1 is x. X out. Any questions on that? So what's good about these is you have a goal in mind. You're like, okay, well, I want to get it to x. What do I need to do to get it there? So you can kind of work until you get there. Alrighty.
So do we have to come up with the inverse, or is it going to give us the inverse? We have to see it right or not.
For these right now, they're going to give you the inverse. You're going to say, like, this is a proposed inverse, verify that it is.
And then eventually we'll have to come up with it.
In a little bit, we're going to see what we come up with. Oh, there we go. Oh, that's all the room I got? Okay, well, we'll work with it. All right, so now we're going to do f inverse of f of x. See if that is x. So we're going to take f inverse, and everywhere there's an x, we're going to replace it with f of x. So we're going to have 1 over f of x plus 1. I don't think this one's going to be as pretty. Yeah, I guess it's not bad. It's not that bad. Then we're going to replace that f of x, which what it actually is just 1 over x minus 1. So this is going to be 1 over x minus 1. And don't get the plus 1 out here. Any questions on setting that up first? All right, so the same thing we did on the, I guess, the last part of the other one. We're not going to worry about the plus 1 on here right now. I just want to get this fraction simplified. Right now I have a fraction containing another fraction. So we're going to multiply the numerator and denominator by that denominator there. So I'm just going to rewrite the whole thing. We're going to have 1 over x minus 1. And I'm going to multiply this numerator by x minus 1. And I'll multiply this denominator by x minus 1. Don't forget the plus 1. So what's going to happen? Well, this and this will reduce, so we're just left with a 1 in that denominator. That's pretty nice. In the numerator, you got 1 times x minus 1, which is just going to be x minus 1. We have x minus 1 over 1 plus 1. And an x minus 1 over 1 is just x minus 1 plus 1. And negative 1 plus a positive 1 is 0, so we end up with just x. So I'm going to rewrite. So both ways we were able to verify, yes, f of f inverse is x, and f inverse of f, they're both x. And so yes, those two functions are inverses of each other. Any questions on that? All right. Oop. That's all there is on there? I guess so. Sorry. My sinuses have been going crazy. All right. So let's talk about the graph of a function and its inverse. So remember that if you have a function and it maps A to B, so like an x value of A mapped to a y value of B, so it has the point A comma B, then the inverse function is going to map B to A. That means it will have the point what? B comma A. So if you have the graph of the function, all you need to do to find the graph of the inverse is to reverse the order pairs. Invert the order pairs. So for this graph here, yeah, but give me a place pointer, I'll show you. You have A sub 1, B sub 1. That means the inverse is going to have B sub 1, A sub 1. You have this point right here, A sub 2, B sub 2. So the inverse is going to have B sub 2, A sub 2. And then it has the point A sub 3, B sub 3 on F. And so the inverse is going to have B sub 3, A sub 3. So all you do is swap the order pairs, just like we did for that first problem when we found the inverse. We had a set of order pairs. Same thing for a graph. You just swap the order pairs. What's interesting about it, though, is you always end up with a graph that is symmetric with respect to that diagonal. And that diagonal, which I wrote over it, is the graph y equals x. So it will be symmetric with respect to that diagonal line. So if this is the graph of my function, f of x, can we graph f inverse? So if the original function has the point -2 comma -1, what is the inverse going to have? -1 comma -2, so that's going to be right here. If the original function has the point -1 comma 0, what is the inverse going to have? 0 comma -1. And if the original function has 2 comma 1, what is the inverse going to have? 1 comma 2, which is up here. So if we connect those together, oh, that was bad. That's okay. We end up with that graph there. That is the graph of the inverse. And you can see this is that diagonal, the symmetry that's happening there. I know it's not a perfect graph, so it doesn't look super symmetric, but you can see. Any questions on that? So it's pretty simple. You're just inverting the order pair. That'll give you, since y'all are doing on my math lab, you'd just be picking the graphs as the inverse to make it a little easier. Actually, than having the graph. It's the same process. Any questions on that? All right. So now to the hard part. Oh, let's skip it. No, I didn't. This is it. How do we find the inverse of a function with the equation? Easy to do with the graph. Easy to do with ordered pairs, stuff like that. But if we are given the equation, it's a little bit more difficult. So we could go through the steps, and then I guess I'll explain kind of each step as we go. So remember, we usually graph functions. We say a y is equal to f of x, right? And so if we're trying to find the inverse, what were we doing on the order pairs? We were inverting the order pairs, right? So instead of x, y, we're switching the y and the x. And so that's the first thing we're gonna do. Well, I guess it's really the second thing we're gonna do is we're gonna swap the x and the y. So the first thing we're gonna do is, if you have a function, you don't have a y in there, right? You just have f of x is equal to, let's say, 2x. There's no y. But where is the y in that? Anybody know? Remember that y is equal to f of x. So the y is just the same thing as f of x. So this is the same thing as y equals 2x. So we rewrite the function, get rid of the function name, and just replace it with y. So if there's g of x, instead of g of x, you write y. H of x, instead of h of x, you write y. That's the first thing. The next thing we're going to do, we're going to actually reverse the x and the y. Just like we did for the order pairs. We swap the x value and the y value. We swap the domain and the range. We're going to do that. So we're going to take the y, swap it for the x, take the x, swap it for the y. And so we're going to end up with is x is equal to 2y. And the reason I changed colors is because this is actually the inverse. We have inverted our function at this point. Now, it's not written like we normally write functions, right? We don't normally write functions as x equals 2y. Usually we solve it for y. That's what we're going to do. We're going to solve for y. And so to solve this one for y, let's rewrite it as with y on the left-hand side, just so it's what we're used to. We'll divide by 2 on both sides. We'll end up with y is equal to x over 2. And then the last thing we're going to do is, instead of writing y, we're going to give our function a name, and we're going to say f inverse is equal to x over 2. If you recall earlier, we did that one. I said it was 1/2 x. That's the same thing as x over 2. Any questions on that? Got it here, got it there. Oh, I forgot the x here. Let me fix that up. I just messed up the name. It should be f inverse of x. Let's not go straight to that one. Try it. So let's say you have a function. G of x is equal to, let's say, 2x minus 5. It's a one-to-one function, and I know that because it's a line, and lines are always increasing. Well, this one, because it has positive slope, is always increasing, and so I know this is one-to-one. They don't usually tell you that in the problem, but I just want to kind of give you a little idea of how we can figure it out. I mean, we have some ability to do that with what we learned so far. And we want to find the inverse. first thing we're gonna do, what do y'all think the first thing we're gonna do? We're gonna write it in terms of y is equal to 2x minus 5. So replace the name of that function with y. We need a y. All right. What are we gonna do next? We're gonna swap x's and y's. That's when we're gonna actually find our inverse. So that means we're gonna have x is equal to 2y minus 5. And the next thing we're gonna do is what? Solve for y. Yep. So let's rewrite it since I wrote that over there. So we want to get y by itself, so let's add 5 to both sides. So we get x plus 5 is equal to 2y, and we'll divide both sides by 2. And so what we'll end up with is y is equal to x plus 5 over 2. And then the last thing we're going to do is what? We're going to replace y with the, let's just say with the name of the inverse. Because in this case, what was the original function called? G. So we're going to call this one g raised to the -1. So g inverse of x is equal to x plus 5 over 2. And that's my inverse function. What's neat is these I don't want to say simple, but these non-complex functions, like let me write. Is you can kind of see the inverse nature there. For g of x, the first thing you do is multiply by 2, and then you subtract 5, right? If you want to walk that back, do the opposite, what would you do? You would add 5 and divide by 2. So you can kind of see it's the opposite instruction set that you would go through, the opposite procedure you would go through for the function. Now, when it gets complicated, some of the I mean, it's difficult to do that, but for these simple ones, I feel like it's kind of neat how that works out. Any questions on that? If we want to test it, we can. I want to do, let's do g of g inverse of x. And so that's going to be 2 times g inverse of x minus 5, which is going to be 2 times x plus 5 over 2 minus 5. And this one's not too hard to see, so you probably see it already. But that 2, those 2's will reduce, and you're just going to have x plus 5 minus 5, which is just going to give you x. So it checks out. Do you have to check them? No, not necessarily. But if you'd like to, you can. And you can check it the other way around as well. The inverse of the original function as well. The inverse of g of x. To get you x as well. That one's probably actually easy. I tried to choose the easier one, but I didn't think about it. Any questions on that? go back to that other example. So here we have a function that's f of x is equal to 2x plus 1 over x minus 1. What makes this more difficult is that you have two x's in your original function. Notice that we had that note there that x cannot equal 1. Anybody knows why that is? Yep, we got a domain issue there. X can't equal 1 because they would have a division by 2. So that's just kind of them covering themselves. Anytime you give a function, you give the domain too. But it is 1-to-1. I'm gonna take their word for it. They say it right here that it is 1-to-1. We could test it if we wanted to, but let's just assume that it is right now. And so what we want to do is we want to find the inverse. So that's what I was gonna say. So, well, let's start off with the first step, right? Let's do we're gonna replace f of x with y. So we'll have y is equal to 2x plus 1 over x minus 1. And so when we swap the x and y, just like you're saying, we're gonna swap every x with every y. So what you end up with is x is equal to 2y plus 1 over y minus 1. Not in that case, because you know why? Okay, so the only time you can reduce a fraction is if what you're reducing by is in every term. So if you had like 2y squared plus y over y to the third, let's say minus y. And in this case, every one of those can be reduced by y. And so this will reduce to 1, this will reduce to 1, that will reduce to just y, and this would be y squared. So it needs to be, everything needs to be reducible by that term. Because they have this, plus 1 and minus 1 here, that's why you can't reduce by y. It's a common mistake. People in my calculus class always do that. I don't know where they got it from, but no. All right. So, what's the next step that we're trying to do? We want to solve for y. How do you think we're going to solve this for y? This is a tough one. Multiply by what? Yep. We're going to multiply both sides by y minus 1. And so we're going to end up with y minus 1 times x is equal, this is reduced, so you have 2y plus 1 left on the right hand side. What do you think we're going to do from there? And we want to solve for y. That means we want to get everything with a y on one side, everything without a y on the other side. That's our goal. Yeah, so we're going to distribute the x because this has a y, but this does not. So I want to be able to move this and this separately. So we're going to distribute that x. We're going to end up with xy minus x equal to 2y plus 1. And a lot of people don't think of doing that. That's why I want to see if I did. So at this point, we got term with a y, term with a y, term without a y, term without a y. Right? That means we need to move everything around. So let's add x to both sides. Doesn't really matter what order you do this in, but So of xy is equal to 2y plus 1 plus x. Let's see. Nope. If I divide it by 2y, that would actually reduce my y's away and I have no y. So how else can I move that 2y? We'll subtract it. So we'll subtract the 2y from both sides. And so we end up with xy minus 2y is equal to what's left over, 1 plus x. And so now we got to where we want to go. Got everything with a y over here on the left-hand side. Everything without a y there on the right-hand side. How can we get y alone, though? This is the tough stuff. This term has a y. This term has a y. What can we do with that y? Do I know? We can factor it out. So we'll have y times what's left over, x minus 2 equals 1 plus x. I should have wrote it as x plus 1. Come on. It doesn't really matter, it just looks better. And then what are we going to do to get y by itself now? You got y times x minus 2. So if you want to get y by itself, we're going to do divide both sides by x minus 2. And we end up with y is equal to 1 plus x over x minus 2. And if we rewrite it now using the actual name, I believe it was f, right? Yep. We'd have f inverse of x is equal to 1 plus x divided by x minus 2. That is my inverse function. Don't forget that last step. You always forget it. I mean, y'all aren't doing paper tests, so maybe you won't have to write that, but there's no always mark on point. Any questions on that? You can kind of see the similarity on that one in the original function. The original function was 2x plus 1 over x minus 1. So like I said, when it gets complex, it's a little hard to see how it kind of walks back, you know, the procedure that you would normally do for that function. All right. If I asked you, what is the domain of f inverse? Can you find me that? We already know the domain of f was let's write it in, no, we'll write it like that. X such that x can equal, I believe, 1, right? Yep. Why can't x equal 2? Yeah, we have a 0 in the denominator there. It's going to be undefined. So for an inverse function, it's x such that x cannot equal 2. Now, here comes my thinking question. What is the range of f? You got one extra number in there. So remember how the relationship between the domain and the range for the function and its inverse, right? The domain of f, let's write it out there. Do I have enough room to write it somewhere? I can write it. The domain of f is equal to the range of f inverse. And the range of f is equal to the domain of f. So if I want to know the range of f, how can I find it? We'll look at the domain of f inverse. The domain of f inverse tells me that x cannot be 2. So what do you think the range of f is going to be? Close. So you're still close. But it's going to be, what can't be 2? Is range determined by an x value? Y value. So it's going to be y such that y cannot equal 2.
So on the test, do we have to write it like
I'm not sure, but I mean, if you did, this would be what? Negative infinity to 1, union 1 to infinity, and this would be negative infinity to 2, union 2 to infinity. I'm not really sure how to do it. I mean, I could go look up a problem and see. We could go look at one afterwards. Any questions on that? What if I wanted to know the range of f inverse? What would that be? Is what? Y can't equal 1, so it'll be y such that y cannot equal 1. Remember, it's the same as the domain of the original function, the domain of f. So it'll be y such that y cannot equal 1. A common mistake is that people put x for the range because they look at that one and go, oh, that one's x, and they put x. So, but remember that range is in terms of y. It's your y value. Switch it to the y. It's telling you what value to take away or what value to be, but you need to determine that it's the y value, it's not the x value. Any questions on that? Oh, we're good. Let's see what we got. I think I cleared that page. Remember that I said for you to find the inverse, the function needs to be 1 to 1, because if it's not, the inverse that you find will not be a function. And if we look at the graph of x squared, I mean, we kind of know what it looks like, right? It's a parabola that opens up. Pretty basic. The vertex is at the origin. Is this a 1 to 1 function? No, because I can draw almost, I mean, any horizontal line I draw above the x-axis is going to hit it twice. Boom, 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 boom. It's going to update at some point for y'all. Let me switch it back to the other share. That's why I don't like using the desktop share, because it's slow. There we go. So you can see it intersects it twice, and so this is not a 1 to 1 function. So in those cases, what we can do is we can restrict the domain of that function. Say, well, we're only going to worry about where that function is greater than 0. I guess it'd be quicker to do this. We're only going to worry about that portion of the graph. So there are some times where they'll take a function, and to make it 1 to 1, they'll domain restrict it. Say, okay, well, this function is not 1 to 1, but hey, if we're just looking at x is greater than or equal to 0 here, it is 1 to 1. And so we can work with that. Any questions on that? Okay, so we're going to take that function, f of x is equal to x squared, and we're going to only work where x is greater than or equal to 0, and we're going to try to find the inverse. So what do you think we're going to do? What are we going to do first? We're going to swap in y for f of x. We're going to replace f of x with y. So we'll have y is equal to x squared. I don't know why I changed colors. Then what are we going to do? We're going to do our swap, which is when we're actually finding the inverse. So we'll have x is equal to y squared. I like to rewrite this in the other order. I just like having my y's on the left hand side. Oh, not 0. Sorry about that. How are we going to solve this for y? Hey, we can do the square root method. But what's going to happen? And close. Remember, whatever variable, the side opposite the variable you're solving for is going to be plus or minus. So we end up with y is equal to plus or minus the square root of x.
So how would that work with x?
Well, let's think about what we have here. We have y is equal to plus or minus the square root of x. Is that a function? It's not. If you put in a value for x, right? If I put in 4 for x there, square root of 4 is 2. So y is going to be plus or minus 2. That's not a function, because if I put in a value for x, I get 2 different outputs. I get 2 different y. So at this point, this one is not a function. But I'm going to run a ring with the word function. But if we think back to saying, well, x has to be greater than or equal to 0, that means that we can get rid of that negative there. So we're going to end up with y is equal to just the square root of x. That is a function. That's good to go. Ooh, hit the scroll bar. Oh, let me write right there. Oh, the whole thing broke. Give me a second. I'm going to refresh the page real quick. Hopefully that fixes it. We're almost done with the problem. Let's see if I can write now. Ah, cool. Okay, so we have our function, but we need to write it as, you know, inverse. So we're going to write it as f inverse of x. Let's see what this goes. And that inverse function is also going to have, well, let's actually graph it and talk about it. So let's write it right here. If I wanted to graph the inverse function there, what do you think it's going to look like? Kind of a tough one. Well, the square root of 0, that's still 0. Square root of 1, that's still 1. The square root of 2, that's tough to do. Square root of 3, that's tough to do. Square root of 4 is 2. All right? So that'll be probably about right here. That graph looks like that parabolic curve, but just coming off the sides. Like that. And so you can still see that it's kind of a symmetry to that diagonal. I didn't draw it perfectly. But that is the graph of that inverse. When we took off that negative part of the square root, we got rid of this part of the graph, which would have made it not a function. That's what we did. So the same thing we kind of did here, where we took off that half of the graph, that domain restriction is also taken off that half of the graph. That would have made it not a function.